Let us now present the algorithm using stochastic gradient descent, which is the algorithm used in practice to train VAE. Note that the function above is the elbow function and is the metric we want to maximize when training our network. First, we initialize the values of theta and lambda with theta 0 and lambda 0. This corresponds to initializing weights and biases in the two neural networks, the encoder at the bottom and the decoder at the top. Then we iterate the following procedure. We randomly choose a sample I. Then we draw MRID samples Zij distributed as Q lambda t z given xi. Note that xi is fixed, so we generate latent variables Zij based on the distribution output by the first network, the encoder. Based on these variables Zij, we compute an empirical version of the elbow defined in equation 103, where we have replaced the expectation by its empirical counterpart. This measure depends on the parameters lambda t and theta t, and we can thus backpropagate the gradient of this metric in the network in order to compute the gradient and to implement a gradient ascent. Indeed, here we want to maximize the metric. With this procedure, we update theta and lambda at the same time and not iteratively, as seen in the previous algorithm. This procedure is then computationally appealing because each step corresponds to a forward and backward path through the whole network. This is classical in neural network training, as we have seen so far in this course. Now, do you see any problem with this procedure? The first question is how to compute the KL divergence. We are going to answer this question later. For now, just keep in mind that this can be computed explicitly when using Gaussian distributions. You can pause the video to look for another problem in this procedure. The other more fundamental problem is the gradient flow in the backpropagation step. In fact, the gradient flow is blocked in the middle of the autoencoder. Indeed, the encoder produces parameters, the mean and covariance, for the distribution of z given x. However, the decoder takes variable z as input and not distributions. The problem is that zi depends randomly on the output of the encoder. The encoder outputs parameters and zi is randomly drawn according to these parameters. To solve this problem, we need to reparameterize the network. Instead of drawing zi from the distribution q lambda z given xi, we let zi be a function of a random variable epsilon I, xi, and lambda. The function itself is deterministic. Epsilon is a random variable, but it is now possible to differentiate zi with respect to lambda. Such a transformation is possible for a Gaussian distribution by letting epsilon distributed as a standard Gaussian random variable and g the function defined below. With this expression, you see that it is easy to differentiate g with respect to mu or sigma, which are the two parameters of interest. We simply need to replace the expectations with respect to q lambda by expectations with respect to p, the distribution of the new random variable epsilon. Consequently, the gradient flow is not blocked anymore, and one can implement a classical backpropagation procedure in this network. We can now state the full procedure. We want to maximize the elbow metric. As before, we initialize the network parameters, theta and lambda. Then we iterate the following procedure. We first sample an index I. Then we generate MRID samples, epsilon ij, from the distribution P, in our case, a standard Gaussian distribution. We then let Zij equal to g epsilon ij xi lambda. Then, using these values, we compute an empirical version of the elbow function. Thanks to the reparameterization trick, we can backpropagate the gradient of the metric through the network and update all parameters at once, following the stochastic gradient descent update. We have no more problems with gradient flow, and this gives you the basic procedure to train a variational autoencoder. To conclude this presentation of VAE, we just need to mention how we can compute the KL divergence in the elbow. We want to solve the above problem. The major result we use is the one in equation 105, which computes the KL divergence between two Gaussian vectors. Since all our distributions are Gaussian, the one output by the encoder and the one output by the decoder, we can directly use this result. Moreover, we have mentioned that it is sufficient to consider latent variables whose components are standard independent Gaussian variables. Therefore, the distribution we put on the latent variables is a Gaussian with mean 0 and covariance matrix equals to the identity. Finally, the result we use to compute the KL inside the elbow is the one given in equation 106. Now, we have seen everything we need to train a variational autoencoder. We have seen the architecture of a VAE and the different ideas behind its optimization. You should now be able to train such networks.